Okay, so welcome to the plenary session and to a special plenary talk. My name is Felix Otto. I'm at the Max Planck Institute for Mathematics and the Sciences in Leipzig, Germany. So special sectional and plenary talks are a new program item for the ICM. One intention was to connect to important developments that involve mathematics, even when they're not driven by card-carrying mathematicians. The idea is to have us exposed to these new horizons for mathematics. A recent and stunning success for mathematics is the experimental proof of the predictive power of the elegant partial differential equations formulated by Einstein, which correctly predicted the form of the gravitational waves emitted by the merger of two black holes. This does not only require breathtaking experimental setups, but also elaborate asymptotic theory, and as we shall see in this talk, highly sophisticated numerical simulations. So it is a pleasure to introduce Franz Pretorius, who is precisely the world expert on this numerical simulations. Franz Pretorius is professor of physics at Princeton University and director of the Princeton Gravity Initiative, which is about 5 years old. His technical expertise is in something the numerical analysts and singularity seekers among us can easily appreciate, namely, for instance, adaptive mesh refinement for hyperbolic PDE. 5 years ago, he was awarded the New Horizons in Physics Prize for his computational work on black hole fusion. Last year, he received the Dirac Medal of the ICTP in good company of Buonanno, Damour, and Tchaikovsky. Franz, we're looking forward to your survey of gravitational waves, please.
Thank you very much, Felix, for that very generous introduction. It's a pleasure to give this talk at the virtual ICM and a great honor. Yeah, so I was asked to give a survey of gravitational waves, and I guess there's a tremendous amount that I could say in many directions. And what I've decided to focus on is, I think what's the most, in my opinion, kind of the most exciting thing about gravitational waves that's unfolded in the last few years, and that is the observation of the universe in gravitational waves. So here's one part of the outline. So the main motivation for sort of everything that I'm going to say is observing the universe in gravitational waves. And why this is, I think, so profound, but why it's also been such a challenge, is that the sources of gravitational waves that we are witnessing now, that the LIGO-Virgo collaboration has been getting data from, is coming from the dynamical strong field regime of general relativity. And this is the first time that we're actually been able to sort of quantitatively probe this rather remarkable regime of Einstein's theory of general relativity. So actually, probably half of the talk is going to be for me just to sort of explain what I mean by this dynamical strong field. I can imagine that this is a very broad audience, and perhaps not many people have sort of looked at general relativity in much detail. So I want to spend a little bit of time sort of explaining what it is and what the strong field is versus the weak field, what gravitational waves are, what the basic properties are, to sort of give you some sense for why I think we're kind of entering a rather remarkable time in science with this observation of the universe in gravitational waves. So the next part of the talk is I want to give some highlights of what we've actually discovered, what gravitational waves have told us about the universe. And I've listed sort of three that are, in my opinion, kind of some of the most profound things that have been learned in the last few years. Though I guess I should apologize, at least for this talk, that I probably only will talk about this first one in much detail. And that is that we now have the first quantifiable evidence for the existence and dynamics of black holes as governed by Einstein's theory. So I want to spend a bit of time, like why, sort of motivating why I personally think that this is such a remarkable advance in the science of general relativity. And not that these other two topics are any less remarkable. So the second one is everything that's been learned from the first observation of two neutron stars colliding, the binary neutron star merger, and then some rather unusual hints at what might be going on in the stellar mass black hole population. So if I can be sufficiently disciplined as I go through my slides in terms of time, I might actually be able to say a little bit about these last two topics. But if not, I have actually commented on this all in the conference proceedings. So I'd encourage people who are more interested in these latter two topics to also browse that. Okay, so let me just sort of set the stage and give sort of a very brief overview of general relativity. So this is Einstein's theory, and it's, I guess we think of it as a theory of gravity, but it's actually a theory about the nature of space and time, or space-time. And it posits that space-time can be described by a geometric construct. And here I think perhaps one of the most convenient ways of representing that is through a generalization of Pythagoras' theorem. So here I've got, just imagine some surface with curvature. We've got a coordinate system x, y, z that I'm labeling with this in this vector notation, sort of x sub a, where a runs over the space and time coordinates. So it includes both time and space. And if we want to understand geometry in this four-dimensional space-time, essentially we need to know the distances both in space and time between any pair of points. And so, of course, because of its curvature can vary at places within the space-time, and so it's most convenient to use this differential form of essentially Pythagoras' theorem that describes distance squared everywhere on this manifold. Now, one thing that's unusual about the geometry that's posited to describe space-time in our universe is that time adds to distance squared in the opposite sense that space does. So this infinitesimal distance squared can be positive, zero, or negative in the so-called Lorentzian manifolds that are relevant for general relativity. And so that's why in general relativity, we never take the square root of this. So this is our Pythagoras' theorem. We always use the squares. We don't want to bother with dealing with complex numbers. And incidentally here, in these tensor expressions, so this GAB, this is the metric tensor that essentially characterizes everything interesting about the geometry. And we use the Einstein summation convention to represent summation. So repeat indices in these expressions represent summation. So that's one important sort of hypothesis in general relativity. Of course, the other, perhaps the more crucial one, or the one that's actually most challenging, and not necessarily more crucial, but both of them are just as important. And one is, okay, so space-time does have this geometric structure, but where does this come from? And that's given by the Einstein field equations that I've written here in tensorial form. So on this left-hand side here, this is capital G, AB. It's called the Einstein tensor. It's a relatively complicated object that's constructed from the Riemann tensor and contractions of the Riemann tensor. And it represents, if you will, it characterizes the geometry, the curvature in the space-time. On the right-hand side, there's a stress energy tensor of any matter fields that might exist in the space-time. And this is multiplied by the fundamental constants of nature. This capital G is the Newton's constant, and little c is the speed of light. So these are any four-dimensional Lorentzian geometry that we think describes the universe, at least classically, must be subject to these set of equations. Of course, they look very simple in tensorial form, but as I mentioned here, kind of the key item describing curvature is the space-time metric, little gab. And so the question is, what is this equation in terms of this metric tensor, which is ultimately what we want to solve for? And if you expand it out, you will find that it's a set of essentially 10 second-order quasi-linear partial differential equations for this metric tensor GAB that we have to solve for. And it's 10 because this Einstein tensor is a symmetric. So in 4 dimensions, 4 by 4, you'd think 16, but it's symmetric. So they're essentially 10 second-order partial differential equations that this represents. So that's the challenge of solving Einstein's equation, is solving this set of 10 nonlinear coupled partial differential equations for the metric tensor. Now, one solution, one simple solution is, well, let's set the matter to 0, so there's no matter, and one solution we get is the following Minkowski spacetime, and this actually is the geometry of special relativity. So special relativity, if you will, is also a theory about the nature of spacetime, But there's no dynamics. The metric is just given a priori. It's got this particular structure. You can see it's a pretty simple generalization of Pythagoras' theorem. The XYZ is sort of your three-dimensional Euclidean space. Here you can explicitly see how time adds with the opposite sign. And there the c is, again, the speed of light. So this is just a constant. And of course, that's so that this equation makes dimensionful sense. Every component is length squared. Okay, so if that's the vacuum solution, well, one of the, well, at least, so this is one solution, but of course, the Einstein equations are nonlinear. And this is not the only vacuum solution. In fact, pretty much everything I'm going to be talking about, except when I get to the neutron stars, if I do, is really all in vacuum. So we don't even have to worry about the matter content. But still, because the equations are nonlinear, there are many more solutions possible than just this, this very special, actually completely flat solution. And so, in some sense, what you can think of it is that because of the nonlinearity, curvature can source itself. You can have interesting solutions, even in the absence of matter creating curvature. And a couple of the most fascinating of these solutions are black holes and gravitational waves. And they're going to feature prominently in the rest of the talk. Okay, so let's first talk a little bit about weak field gravity, and let's start with gravitational waves. So gravitational waves, again, now they're solutions to the vacuum Einstein equations, but what we want to think here of, let's solve these analytically, but these are complicated equations. We can't do that in general. In general, we do need some numerical methods. And unfortunately, I'm not going to speak too much about that, but at least in certain cases, we can get some analytic traction on the field equations. And for linear cases, we can do perturbation theory. So here, for example, to uncover the nature of gravitational waves in this weak field. So by weak field, in some sense, I mean when linearity, when the solutions are well described by linear perturbations. So we think of the metric as being this eta AB, which is just this Minkowski space-time. And then we add some perturbation, we keep it small, we plug it into the Einstein equations. And the interesting thing is you find that you get these solutions that represents wave-like phenomena, sort of, or ripples in the geometry of space-time, if you will. You find that they propagate at the speed of light. And interestingly, the Einstein equations tell you that there are two so-called linearly independent solutions, or what we commonly call polarizations, in any particular direction of propagation. And they call the plus and the cross polarization, for reasons that should be clear on the next slide. But so, for example, here is a solution for a wave that's traveling in the z direction. It's traveling at the speed of light. So this h plus, this is sort of the amplitude function representing the plus polarization. It's a function of t minus z over c. So this is a wave propagating in the plus z direction. Similarly for the cross polarization. And this is the components of the metric that these waves excite. So if you kind of stare at this for a little bit of a while, you'll find out, well, how is this changing the geometry? What is these ripples in space-time geometry that this represents? And you'll find the following. So what I'm showing here is just sort of imagine a ring of test particles. So they're on geodesics, and they're in the XY plane. And imagine that this wave is now a wave that's traveling in the z direction. So it's traveling sort of orthogonal to this plane. And the interesting thing about how gravitational waves and general relativity affect these particles is it only distorts space-time transverse to the direction of propagation. So it doesn't have any longitudinal perturbations, it's transverse. So it only affects things in the XY plane here. And on this top row, I'm sort of depicting schematically what a plus polarized wave would do, say sinusoidal plus polarized wave. So you take an initially circular ring of particles, it's going to sort of cyclically stretch and squeeze this ring of particles, but in direction, sort of in the ellipses of the stretching and squeezing is aligned with the XY axis. The cross polarization depicted at the bottom is qualitatively exactly the same, except the distortions are rotated by 45 degrees about the z-axis relative to the plus polarization. So in general, if you have a wave propagating in the z direction, there's going to be some arbitrary superposition of these two modes of oscillation of space-time that are present. So that's sort of the weak field nature of gravitational waves, at least in terms of the metric. But of course, these waves do carry energy. And here's an expression for the energy flux that is emitted to the energy per unit area per unit time. Again, here is the speed of light. It's coming in c cubed. This is Newton's constant again, so just the constants of nature. And here, this is an expression that shouldn't be a surprise to people, especially it's very similar to electromagnetism or energy in a scalar field. It's just the sum of the squares of, in this case, the time derivatives of these two polarizations. What's a little bit unusual here is that we have to time average, but essentially just the sum of the squares of the amplitudes of these waves. But one thing I wanted to point out and why I've sort of put in these dimensional constants is, so C is a large number, G is a small number in our standard units of measurement. And so this is a huge number that's multiplying this, the actual amplitudes of the gravitational waves, 10 to the 35 joule seconds per meter squared. And so what this is telling you is that space-time is, in some sense, very, very stiff. That if we, sort of the amount of energy that even a relatively small perturbation carries is huge. Or conversely, if we wanted to create a perturbation that was noticeable, the amount of energy you'd have to put into it would be tremendous. So space-time doesn't like to be bent. It likes to be close to Minkowski as much as possible, at least in terms of energy. So another way to see this, and this gets to another aspect about gravitational waves, is so that what we just spoke about is what happens when a gravitational wave is there, when it propagates, what's its energy content, but how are they produced? Well, one way of producing them, and this leads, again, this comes from linear perturbation theory, leading to the famous quadrupole formula, is if there are asymmetric accelerations of energy. And actually in this formula, we can actually think of actual matter, but it could also just be gravitational energy by itself. And so what I'm sort of depicting here, so this rho of TR, here's some matter, rho is the energy density. If it accelerates in some asymmetric fashion, it will produce gravitational waves. And this is the leading order expression for the metric perturbation that acceleration would produce. So a few things that you notice about this. So if these waves decay like 1 over r from the distance to the source, which is not surprising. That's consistent with energy conservation, as you know, the previous expression that I gave. Again, they travel at the speed of light, but you're in the radial, they sort of propagate out radially from the source. But one interesting thing here is that what controls the magnitude of this perturbation is an accelerating quadrupole moment of the source. So notice the two double dots there that represents time derivatives. So there are two time derivatives here. Xi and xj are actual spatial coordinates. So this integral over the spatial distribution is sort of measuring the quadrupole asymmetry of the source. And so what this is telling you is that in general relativity, you need some asymmetric acceleration. It can't be spherically symmetric. There can't just be a dipole component. You need at least a quadrupole structure to the source, and it needs to accelerate. But then again, another interesting thing about this formula, which is sort of similar to this expression that I mentioned here, and here now they coming in, it's the opposite side. This is now the generation of the waves. But again, now G is a small number, C is a large number. So this, in terms of units, we know is an incredibly small number. So this is perhaps more explicitly telling you how difficult it is to produce gravitational waves that could be measured. So you have to have a tremendous amount of either energy density or very rapid acceleration to overcome this incredibly small number to get a perturbation which might be, in principle, even measured. So in some sense, gravitational waves are no different from electromagnetic waves. And you can say, well, why don't we build like gravitational wave emitters and receivers like we do with radio waves, etc. And the problem are these incredibly small or inversely incredibly large numbers that show up here. The amount of energy that it would take to produce a gravitational waves that we might observe is just unimaginable, and it's impractical technologically to do that on Earth. And so that, in some ways, that's why we kind of have to go to look at to the universe for places where these things, the accelerations and the energy densities might get extreme enough where we can actually, they could produce such incredibly large amounts of gravitational waves that we could observe them. But even so, it's a tremendous technological challenge. And that was one of the amazing things of the Virgo detectors, that they actually overcame some of these technological challenges and ushered us into this era of gravitational wave detection. Okay, so one thing is, okay, so I've described a theory, it's been known for a while, but is this correct? Does nature actually work that way? And actually for a long time now, we've known that this weak field description of space and time as described by relativity is in fact, there's very strong observational evidence that it is correct. And the most famous is this Hulse-Taylor binary pulsar that Hulse and Taylor were awarded the Nobel Prize for in 1993. And so essentially what this is it's an observation of a neutron star in a binary system. It's a pulsar, so it's emitting very regular pulses with a sufficiently sort of high regularity that we can get very accurate measurements of the orbit of this binary system. Now, this binary system, this does have a time-varying quadrupole moment, so it is emitting gravitational waves. Those waves are carrying energy away from the system. And so if you sort of combine all of these properties, the propagation of gravitational waves, the energy content, the quadrupole formula, you should expect, and then sort of anticipate how that feeds back on the binary, that the orbit should decay. They should get closer to each other. The period should increase with time by an amount that's consistent with all of this energy balance and gravitational wave emission. And this is what this figure on the right is showing. And actually what's so remarkable about this data is that that line that goes through all the observation points is not a fit to the data. It's the actual prediction. So in this kind of a weak field situation, this is quite a stunning confirmation that this aspect of space-time is as described by general relativity. Okay, so why aren't we done there? Why isn't that telling us that, yes, general relativity is kind of how things work in general? And the reason why that's not enough is because there is a strong field regime to general relativity, which is actually qualitatively and fundamentally different from the weak field regime. It's also, from a physics theory perspective, it's actually a very unusual strong field as well. So in all the other fundamental theories of nature that we know of, the strong weak force, the electromagnetic field, QED, etc., when qualitatively new phenomena typically showing at some new energy scale or new length scale that is a property of the theory. There's some fundamental constant that determines the new scale. In general relativity, there is no dimension length constant in the theory. So again, this is a theory of geometry. So if there were some interesting scale that you put in by hand in the theory, that should have a dimension length constant, but there is none. So of course, Newton's constant and the speed of light enter, but these aren't really sort of dimension length constants that describe when something new should arise. Yet general relativity does have a regime where new phenomena arises. And it's not because of any length scale that you put into the theory, it's because the equations are nonlinear. So it's nonlinearity that actually gives you sort of qualitatively different solutions, when curvatures are small in some sense versus large. Now, it's not easy to actually explicitly define what this is, but in a couple of situations, we can have kind of a nice heuristic characterization of that. And one is in near spherical, not spherically symmetric, but kind of a spherical sort of, if we take a spherical distribution of matter, and this is sort of how a length scale arises here in particular comes through Thorne's hoop conjecture. So the idea is here, okay, so how do we get to the nonlinear regime? Well, let's take a certain amount of energy. So this little orangey blob here, just imagine that's amount of energy. And actually the most appropriate thing to think of is energy, not necessarily matter energy. So we want to think of E equals mc squared. So it's actually energy that's important here. So you can think of matter, but it's also energy. So this could be pure space-time energy, or it could actually be matter. And so we have a certain amount of energy here, which has a mass m. And this capital R is this hoop that encloses the matter completely. So it's a spherical hoop that in all directions encloses the matter. But then also one property of the matter, so we know what its mass is, we know what this, so at least we know what this mass is, so we can compute this quantity here called the Swatch of Radius. And again, G and C are these fundamental constants, so there's Newton's constant, the speed of light, so it's really, just this proportional to the mass of the object. And that's now going to define a radius. And if this radius, the so-called Swatch of Radius is smaller than the actual radius of the object, we're in the weak field. If it's larger, we're in the strong field. Okay, so at least one thing you can imagine, like let's say we start in the weak field. How do we get to the strong field? Well, one thing is we can try to compress this mass all the way such that it crosses its Swatch of Radius, or we can just add a lot more matter such that the Swatch of Radius grows and it exceeds the actual radius of the object. So what is qualitatively different about space-time? What happens when we actually go to the strong field regime? Well, the nature of space-time qualitatively changes. The interior of the space-time becomes intrinsically dynamical. It doesn't matter what you try to do to keep that matter sort of sitting where it is. Space-time doesn't allow it. Space-time becomes dynamical and starts to flow towards some kind of a singularity that forms. This interior part of the space-time becomes causally disconnected to the exterior. If you have exterior stationary observers that are trying to look at what's happening, they will start to experience increasing time dilation relative to distant observers. So their clocks will start running slower and slower. And at the point that time dilation will become infinite as you approach the Swatch of Radius. And there are many other interesting things that happen, but basically everything that I've described here, I could have just said much more simply is, well, when you cross the strong field regime, a black hole forms. But of course, why I did it this way is that black hole is really a fascinating solution to the field equation that's got a remarkable geometry that's given by a lot of these properties. And that's kind of what happens when we cross this nonlinear threshold. The character of space-time changes quite drastically. Okay, so now, I mean, sort of the dynamical strong field regime. So what about dynamics? So what about the strong field in terms of gravitational waves? So for example, the quadrupole formula. Perhaps one sort of tried definition of the strong field in this case is, well, when the perturbation becomes of order unity, that's just by definition of perturbation theory. And that's actually not too bad in this case. It does quantify when strong field dynamics occurs. But actually one thing that's kind of interesting about that is, if you just do sort of dimensional analysis or the back of the envelope calculations, you'll find that when this perturbation becomes of order unity, the gravitational wave luminosity in the source should approach the Planck luminosity. It's given by this quantity. So Planck units it's a system of units that are built from the simplest combinations of the fundamental constants of nature. So speed of light, Newton's constant, Planck's constant, etc. So all the fundamental constants of nature, just combine them in the simplest possible way to come up with a system of units. And why this is actually so interesting is usually we think of the Planck units as being associated with the Planck scale, which is supposedly a scale of quantum gravity. But notice here the Planck luminosity, there's no h bar. So Planck's constant, h or h bar, that's the hallmark of quantum. But here the Planck luminosity does, of course, and perhaps it shouldn't be here if this is in general relativity. But the remarkable thing is that even though there is no, quantum gravity scale that general relativity knows about, there does seem to be a limiting luminosity. And what happens with, when you try to, when you have a source that produces energy above the Planck luminosity, well, the actual energy of gravitational waves would be so large that this Hooke conjecture argument would say that the gravitational waves that are being produced would be so strong that they would cause a black hole to form. So if you try to radiate at above the Planck luminosity, basically general relativity says whatever's trying to produce that must be censored and hidden behind a black hole. Okay, so how do we, in a practical sense, get to such nonlinear dynamical space-times? And again, as I mentioned, because of those ridiculously small or large dimensional constants that multiply those formulas, we can't do it on Earth. So we kind of have to look to the universe for possible sources. And there actually is one possible source that does do this, and that's the merger of two black holes. So again, with the quadrupole formula, we want as dense an amount of matter as possible that's accelerating as fast as we can. We've just seen from these Hooke conjecture arguments that we can't make matter denser than a black hole. If we do, it's going to collapse to a black hole. So that's about as dense as we can make matter, energy, and general relativity. And so let's put these two black holes in an orbit. And when they're in an orbit, this is going to be a time-varying quadrupole moment. If they're very close to each other, they could be traveling very fast, close to the speed of light. So they could be producing a lot of energy. And if you do that, you just verbatim use a quadrupole formula, you get this expression for the luminosity of a binary. Again, lots of constants, lots of numbers. Let me just point out this one interesting fact about it is that the luminosity scales as quite a high power of the separation between the objects. So 1 over the separation d to the 5th power. So on one hand, that says, okay, the further apart these black holes are, the luminosity gets very, very weak, very fast. Conversely, the closer they are, the luminosity gets very strong. So if we can use this as an estimate, so perhaps you can imagine the highest luminosity in this in-spiral, and they spiral in for the same reason as the Hulse-Taylor pulsar does, is as they're orbiting, they're losing energy to gravitational waves, so they spiral inwards. And you can imagine, well, what might be the maximum luminosity? Well, that's when the distance d becomes such that their 2 Swatch of Radii are touching. And that's not a very heuristic kind of way of thinking about it, but we can just do that. And then we find that actually, that with these so-called quasi-circular in-spirals, that only reaches about 10 to the minus 3, that of the Planck luminosity. And actually that's confirmed by full numerical simulations that go beyond these approximations. And again, so I don't have time to talk about the simulations, but that in some sense they only reach 1,000th of the Planck luminosity. But only is in quotes here because, well, the Planck luminosity in actual units is 23 times, sorry, 10 to the 26 times the luminosity of the sun. So 1,000th, the Planck luminosity is a luminosity that's as bright in gravitational waves as 10 to the 23 suns. And in fact, 10 to the 23 is order of magnitude the number of visible stars in the universe. So when 2 black holes finally merge, they actually emit in energy as much, well, their luminosity is as bright as all the stars in the universe combined, which is, it sounds like a ridiculous statement, but it's right there. So actually, so what happens in terms of dynamical nonlinearity in a merger? Okay, it's not that the luminosity reaches the Planck scale, but it's at this point particle approximation for the quadrupole formula completely breaks down. And the essential nonlinearity in a merger is what happens as 2 horizons fuse together. And actually that we definitely need numerical methods to solve these 10 coupled partial differential equations for to describe. So we have no sort of perturbative or analytic scheme where we can actually solve the equations in this fully dynamical nonlinear regime. Okay, so that brings me again to LIGO. So when I described the weak field properties, I said, okay, that's very interesting. Does nature behave that way? And thanks to the Hulse-Taylor binary pulsar, we've got good evidence that it does. And I've described some of the strong field predictions of relativity, and at least in my opinion, the predictions of black holes, singularities, causal disconnection sounds incredibly bizarre. It's fascinating, but it's a bit ridiculous. And so we say, well, does the universe actually behave that way? Do we have evidence that it does? And until 2015, with LIGO's detection of the waveforms from suspected mergers, we didn't have any quantitative evidence, but now we have. And so LIGO has sort of ushered us into this new era of observation of the universe, but in particular seeing sources that are coming directly from this dynamical strong field. So this is kind of a remarkable period that we've just entered, just the beginning of this new era. And here on the slide, I've got a snapshot of several events that LIGO has already detected. By now, it's close to 100 events. Most of them are binary black hole mergers. So this one on the top left, that's the first one that was discovered. And you can see these wiggles of the gravitational waves. I'll show a simulation in the next slide that perhaps illustrate this a little bit better. But these are these oscillatory stretching and squeezings that LIGO is seeing here from an event that occurred over 1 billion light years away. So there's been a lot of that 1 over r decay. So it's an incredibly small signal here, but LIGO is, the technology is remarkable that it's able to detect that. And a few other events, and this one here is this binary neutron star that I might say 1 or 2 words about. Well, let me give you sort of a simulation. And incidentally, so we use the word simulation, but this is not simulation in the same sense as, say, it's used more colloquially. These are actually numerical solutions to the full Einstein equations. We aren't simulating anything. We're actually solving the PDEs. So here's a simulation by the SXX collaboration of this particular event. So they pick parameters. So a 36 and 29 solar mass black hole that collided, that produced that, or at least the signal that LIGO said is consistent with the waves that were from the simulation. So that's how we know, that's how we interpret this event. It matches this particular simulation the best. And so that's sort of the interpretation. This is now a simulation of the full Einstein equations, solving for the metric. And what's now a depiction here is sort of one particular representation using one of these so-called Newman-Penrose constants that characterizes the gravitational waves. And this is through a slice of the full space-time that cuts through the equator of this binary black hole system. Now, the masses of those black holes translate to Swatch of Radius of around 100 kilometers or so. So these two little black sort of circles here in this figure are the actual representations of the black hole. So these are the kind of on 100 kilometer scales. This is like 1,000 kilometers if you were to scale this. So this is on something like a 10,000 kilometer squared thing if you want to scale it to real-time units. So this is very close to the merger where I'm going to start this. And here they actually are traveling 30–40% the speed of light. So they're really orbiting each other very fast. So this thing is slowed down by about a factor of 100 times. The actual full simulation only lasts about 40 milliseconds. Okay, now I'm going to... okay, so this little green fuzzy is the gravitational waves. Okay, now I'm starting it. You can see they orbit. They're emitting gravitational waves. But as they're getting closer, the green fuzz is getting brighter. That's because of this 1/d to the 5th enhancement. But it's kind of a runaway process. And eventually it's going to reach this last phase where they're going to plunge together. The horizons are going to merge. It's an incredibly brief period. And there it is. They fuse together and it releases this burst of radiation. And then it settles down to this quiescent stationary Kerr black hole. Switch back to my pointer. Okay, so this is sort of, okay, this is kind of the full solution. These waves are propagating out through the universe. LIGO's sitting 1 billion light years away. And as this wave passes, it's creating these oscillations. LIGO's measuring it. And from that, we can interpret what we're seeing. So now let me describe, the first, again, what I mentioned, like the first sort of, in my opinion, or perhaps the first major discovery from this LIGO observations is that we actually saw this particular wiggle that represents the merger of two black holes. So this is, the first quantifiable evidence for the existence of black holes as described by general relativity, and more specifically about the dynamics of two black holes and how they fuse in this very nonlinear regime. So let me, but before actually showing you a little bit of that data, let me just sort of motivate this a little bit more. So why might we be skeptical of relativity in this regime? So one reason is, of course, just basic scientific inquiry. Scientific theory isn't just as good as its theory. Even if it's a beautiful theory, we need some evidence that this is actually what's happening in nature. And as I've tried to sort of mention, everything else we knew about relativity before, whether it comes from the solar system, deflection of light, the perihelion precession of Mercury, binary pulsars, it's all weak field and qualitatively very different from this other regime of relativity where black holes exist. So we have no evidence for that very kind of bizarre part of relativity. So we really need to test this theory. So it's basic scientific inquiry. On the other hand, there is some data that might give us some pause to question whether relativity really does have a strong field. Relativity does, but whether nature actually is consistent with relativity in that strong field. And that's the puzzle of dark energy together with the scale-free nature of general relativity. So let me explain that briefly in more detail. So what is dark energy? I'm sure you've all heard about this, but that is essentially the observation that the rate of expansion of the universe today is accelerating, which is a little bit bizarre if you think of, well, okay, general relativity is a theory of space-time, but kind of schematically, it should be a theory of gravity. Gravity is attractive. So if our universe is expanding, the attraction due to gravity should be slowing things down, but the universe isn't slowing down, it's expanding. So why is that called dark energy? Well, essentially, the reason is we assume that Einstein's gravity is correct on the large scales that describe the cosmos. And observations suggest that on large scales, the cosmos is on average homogeneous and isotropic, and it's given by the so-called Friedmann-Robertson-Lemaitre-Walker metrics. And if you plug the Einstein equations with such a metric ansatz, you get what's called the Friedmann equations. And so if we assume that Einstein's gravity is correct, so we assume that nothing is wrong with the field equations, we can't compare it to the data, we actually find that we get a huge fraction of, the equation is wrong, there's something that's missing. And so the usual interpretation is, well, there's some missing energy on the right-hand side that must be responsible for this acceleration, and that's called dark energy. But of course, we have no other evidence for dark energy. It's really just coming from this assumption that Einstein gravity is correct on these scales. And so you might question, well, perhaps there's something wrong with Einstein's gravity on these scales. And one thing where, I think we might want to take that a little bit more seriously is to ask, well, in what regime of general relativity are we in the universe on those large scales? And it turns out that on the scales of the Hubble radius, which is roughly the size of the universe, we are in the strong field regime, as described by the Hooke conjecture. So let me just roughly give you the back of the envelope argument for that. So let's go back to the Hooke conjecture. Now we imagine, it's a very simplistic proxy for our universe. So let's just take sort of a uniform distribution of matter with an energy density rho, and let's just make that sort of the energy density of the average energy density in our universe. This is a very small density. And now let's put this in an asymptotically fat space-time within a ball of radius r, just rho, its mass is 4/3, rho r cubed, just the usual definition of density. And this is the Swatch of Radius of this distribution. So then plugging in what the mass is in terms of the density, we get this relationship. And the interesting thing, though, with the Swatch of Radius is it scales linearly with the mass. Or if you plug this r cubed in, it scales like 1 over the density squared. So now imagine, let's just add more and more matter to a larger and larger radius. We will find that keeping the density constant and small, not changing the density at all, but we're just increasing the amount of mass, at some point we should form a black hole when the radius reaches this particular value. Okay, so now the second part of this is applying this to the universe. So again, the radius of the universe is roughly this thing called the Hubble radius, which is the speed of light divided by this Hubble parameter, h. And h represents sort of the fractional rate of change of the size of the universe with respect to time. So the rate of change, the fractional rate of change of the scale factor of the universe, if you will. And essentially for such a simplistic model of the universe, again, it's just back of the envelope, but it's sort of to illustrate this point, this is the Friedmann equation. That tells you how the rate of change of the universe is governed by the matter. So now what we can relate the radius of the universe, which is one of those Hubble parameters, the density, and we find that when we get that our argument for when a black hole should form is precisely this Hubble radius parameter that tells us what the size of the universe is. So for density that's as small, 10 to the minus 20 something grams per cubic centimeter, whatever it is, if we take a ball of that's so large, in an asymptotically fat space-time, if we made a ball of radius, the Hubble radius, it would form a black hole. Now, of course, we're not in a black hole. The point of this thing is not to say that we're in a black hole. I mean, you could perhaps argue that perhaps we are actually in the white hole part. The observations in our universe suggest actually that this is not, that we actually are in a completely different space-time. But the point of this whole argument is the only reason why we can argue we aren't in a black hole is if we're in the strong field or regime of relativity and another solution exists. And this other solution is this Friedmann-Robertson-Walker expanding space-time. But this all essentially relies then on, understanding general relativity in the strong field regime, even though the scales are very different from the kilometer scales of astrophysical black holes. From general relativity's perspective, it's just a strong field on scales of the Hubble radius as it is on scales of black hole horizons. So if we don't know that relativity is correct for the horizons of black holes, we don't necessarily know that it's correct on the scales of the universe and vice versa. So I think, this is, perhaps, you can argue about how good a motivation this is, but I think, dark energy does give us some, I would say, some reasonable pause to say, let's make sure we really understand relativity on the scales of where it considers itself to be strong field. And one place we can do that is black hole mergers. Okay, so let me just say, so what is the evidence for the strong field nature? I just should also mention that the evidence for the existence of black holes has been growing for decades, and this was recently awarded the Nobel Prize, both for the theory side with Roger Penrose and then Andrea Ghez and Reinhard Genzel for the observations of orbits around the center of our galaxy. But this evidence has all been circumstantial in the sense that what it's really telling us is that there are dark, compact objects in the universe that are consistent with black holes if relativity is correct. But it's not a direct observation in the same sense that the LIGO observations is, which I will sort of describe now. So it's like, how do we get a direct measurement of strong field gravity? Well, essentially, the only way we can really do this, is in the light or the sound that this theory emits at, and that's gravitational waves. And if we can observe gravitational waves that come from strong field dynamics. And so this is sort of another illustration of the gravitational waves from this first event. And just what to illustrate the different regimes. So this green curve here is from a numerical simulation of as what I showed. So this is the prediction of this gravitational wave coming from a binary merger. This is the in-spiral part where we can apply quadrupole physics. This late part is that ring down, like when it's settled down to a quiescent curve black hole, which we can also use perturbation theory for. This merger, this is the fusion of the two horizons. And again, that's the most nonlinear aspect of this problem that's manifest in a binary black hole merger, and that's sort of producing this largest burst of radiation. And what I'm also showing here is, so that the LIGO detectors, they have a frequency-dependent sensitivity. So they're actually only sensitive to a certain narrow range of frequencies. If you go to smaller frequencies, they lose sensitivity. If you go to higher frequencies, they lose sensitivity. So there's a sweet spot where they are most sensitive. And quite fortuitously, this first event, that sweet spot of sensitivity landed right on this merger regime. And so then what these other two curves are showing is if we take this numerical simulation and we filter it with a frequency response of LIGO, including noise, that's these other two curves that we get. So these are the two different, one is the actual LIGO curve, one is the actual LIGO measurement, and one is the actual simulation filtered with the noise curves. And so you can see that just on the frequency sensitivity, the in-spiral is suppressed, but all of the signal is essentially coming from this most nonlinear merger regime. And that's actually, that's fantastic for testing general relativity in this regime. So most of the signal is coming from this dynamical nonlinear regime. So how do we quantitatively test it? Now we can just by eye, it looks good, but can we come up with something more quantitative? And the answer is yes. And essentially the mathematical reason sort of why we can do this is because of the so-called uniqueness or no-hair theorems in general relativity. So it's kind of a remarkable property of black holes in relativity that they can't have structure. So when gravitational collapse happens, when black holes form, there can be a lot of dynamics in the process of formation, but they very, very quickly settle down to this quiescent Kerr state, which is described by a relatively small set of numbers, which means that all black holes that could possibly occur in general relativity, and they can therefore possibly be involved in mergers, are governed by a very small set of numbers. Essentially, the initial masses and spins, orbital eccentricity of this binary. So there are a very small set of numbers that govern every single possible merger that might be out there. So if we can compute waveforms for this relatively small dimensional parameter space, And then the wiggles that LIGO see, we sort of filter, or we compare it with this template bank of libraries. And if we then find that there's something that's inconsistent with that template bank, that wouldn't be that we've discovered a new kind of black hole. It will mean that it's something that's inconsistent with relativity. So the fact that there is this uniqueness properties of black holes means that we can cover all the black hole possibilities. And then if we discover something that's novel, it must mean that there's something, or there's some novel aspect of the event that the theory is missing. Inverting that, then, if we don't see something novel, that's how we get these powerful tests of relativity. So one approach is kind of the whole kitchen sink, as I mentioned. We've got this full template bank. We take the observed signal, we subtract it from the filtered template. We see, is the residual consistent with noise? If it is, we say, okay, it's consistent with relativity. You can quantify that in a little bit. But perhaps a more instructive way to sort of see what's going on is to perhaps tease apart pieces of the signal and characterize them by properties we know from merger dynamics. So, for example, we can look separately at this in-spiral phase, which is sort of a linear, these sort of perturbative methods, we know about that. We can look separately at this ring-down phase. And again, if it's fundamentally a small set of numbers that's controlling it, even it doesn't matter how high the signal-to-noise ratio is, how much actual information there is in the data, fundamentally there is really not much information there. So there should be a lot of redundant information. And that's how this particular test I'm now going to describe works. And so here's some sort of quantification of how consistent these signals are with dynamical strong field gravity. So again, from the in-spiral, so here what the LIGO people did is they just looked at this in-spiral portion of the waveform. Okay, there's not much here, but there's enough where you can actually get an estimate of what the two initial black hole masses were and estimates on their spin. So you can get estimates of the progenitors for these systems. Then you can say, okay, so now we have estimates of the initial conditions of this binary, essentially. We can use the Einstein equations and evolve this forwards in time till we get to the remnant. And then we can say then we can predict, well, what should the final mass and the spin of this system be? So that gives us one, sort of taking a little bit of the data, we get one measurement, if you will, of the final mass and the spin, if Einstein gravity is correct. The second independent estimate of the final mass and spin comes from this ring down portion of the wave. And that is, again, because of the uniqueness properties of black holes, the frequencies and decay constants of all the ring down modes of a Kerr black hole, that's a rotating black hole, are uniquely determined by the final mass and spin of the black hole. So inverting that, if we measure how rapidly this wave decays, we get a second estimate of the mass and spin of the black hole. And again, if this is now governed by relativity, if this unique properties hold, that must be exactly consistent with the part that just looked at this in-spiral data. And that's what LIGO Virgo did with these things, and that's what this curve is showing. So yeah, this is sort of this chi, if that's a projection of the spin of the remnant onto the orbital plane, that's what it's most sensitive to. And this is the difference, delta chi normalized to the maximum value is between these two distinct measurements. So of course, if relativity is correct, it should be around 0. And similarly thing for the final mass, the two different estimates of the mass, it should be consistent with 0. Each one of these contours is the result that you get from taking a single piece of data. So for example, one of these observations gives you a pretty large contour. So this has been normalized in some sense that all possibilities should fit within this box. So you can see each individual event by itself is giving a quantitative consistency that's only perhaps 30–40%. So it's not a very high accuracy confirmation. But again, now if we say that these are all these individual events that LIGO have seen, that are matching these black hole merger templates, well, they're all just also basically the same kind of event. There's no difference other than the masses and the spins of the black holes. So all of these events should in some sense also be qualitatively the same. And so we can stack this observation. And if they do that, so if you combine all of these things, you can improve the accuracy. And that's what this little central contour is showing. So if you stack all of the observations where they can make these individual events, you get a pretty tight constraint. And again, that's also, in some sense, to justify the stacking, is also saying that relativity is, this is governed by relativity, and therefore these systems are all similar and we can't stack them. So it's a pretty strong constraint right now for the predictions of relativity. Okay, so as I anticipated, so it's, I'm 55 minutes into my talk and I've got 2 of the highlights left. So I'm not going to actually describe these things in much detail. I'll just spend 1 minute on each of them. And again, apologies, but if you're interested in more of this, please look at the precedings article where I try to go through a lot of this in more detail. But so the second highlight is this event that I'm showing here is where LIGO observed the merger of 2 neutron stars. So now this is actually including right-hand side on the Einstein equation, so including some matter TAV, and this is the merger of these 2 black holes. And this is the time in the time frequency domain. You can see this in spiral track, which actually sort of tracks the quadrupole prediction quite well. What was remarkable about this event, and now because there's matter, there can actually be sort of electromagnetic fireworks. So black holes they only emit gravitational waves. We don't expect there to be much matter around. So we only expect it to be visible in gravitational waves. But with binary neutron stars, in principle, it's going to produce a whole bunch of other observables, and they were discovered. So a gamma ray burst was seen within a couple of seconds of this. Eventually, an optical afterglow was seen. This was perhaps one of the largest astronomical observational campaigns following this event to find this afterglow of this massive explosion as the neutron stars collided with each other. And numerous interesting things that came from this. Just a few highlights. One, this, because the gamma ray burst, because the gamma ray burst came coincidentally with the electromagnetic observation, you can put an estimate of the speed of light that was, a measurement of the speed of light to within 1 part in 10 to the 15. A kilonova was observed. And the interesting thing about that is kind of the source of sort of heavy elements in our universe. So the remnant of binary neutron stars produces things like gold and platinum, and it's actually consistent with the observed solar system abundances. So the gold and platinum that we have here are kind of ashes of the remnants of binary neutron star mergers. There are various other things that I don't have time for. So a lot of very interesting things were observed. And again, let me skip this. And also, there's some interesting things about the stellar mass black hole population. But again, so my apologies for the time, and my apologies for not turning off one of these devices so that went off in the background. And so let me then just, in the last minute, let me just get to the conclusions. Okay, so what I want to conclude with in the last couple of minutes is not to sort of rehash what I've said, but kind of actually just to look a little bit towards the future. So LIGO's just opened up this gravitational wave window into the universe. So what can we expect in the next 5 to 10 years? So this is sort of just the beginning. And I think it's going to be a very exciting time, in the next 5 to 10 years. And that's one, because the LIGO detectors aren't yet at their design sensitivity. The next observing run is expected to begin at the end of this year or early next year. And even reaching design sensitivity, this is as planned, it's going to be about a factor of 2 to 3 improvement in what we have now. There's a next generation of detectors that should give sort of a factor of 10 improvement in sensitivity. So what's the big deal of a factor of 10? But what's kind of remarkable about this, gravitational waves go like 1 over the distance from the source. A factor of 10 implies that we might be able to see it 10 times further away. And remember, I sort of briefly mentioned that this event was observed at about 400 megaparsecs. An estimate of the size of the universe is 10 times that, 4 gigaparsecs. So we get a factor of 10 improvement. We can see black hole mergers of this style that occurred throughout the observable universe in our past light cones. So that will be an astonishing sort of leap. We'll be able to observe essentially the entire universe in gravitational waves for these stellar mass black hole mergers. And other things that are sort of interesting, and again, this is intentionally I did not put slides to discuss cosmic microwave background and pulsar timing. But these are a couple of other observations that people are using to try to observe the universe. And they're also going to, in the next 10 years, going to come up with very interesting, at least lower limits. So it's not just the ground-based gravitational wave detectors that we use to observe the universe in gravitational waves. That's also the cosmic microwave background and pulsar timing. And within the next years, they haven't detected anything yet, but they should get to sensitivities where some very interesting limits will be placed, for example, on inflation with the cosmic microwave background. Again, so apologies. In this case, I didn't actually plan to talk about this. I'm just mentioning it here, but I do describe this in the conference proceedings. So again, if you're interested, please look at that. So thank you very much for your time. And as I understand it, I will now try to go over to that other chat room, and if there are questions, I'll be able to answer questions in that chat room if I can get that bit of technology to work. Thank you.
Yeah, thank you. With a number of well-chosen back-of-the-envelope arguments and kind of displaying the clear logic of verification of the Einstein theory. Yeah, thanks also to the audience. I think the time is over, and as Franz Pretorius said, he will be ready to answer questions in the Discord, on the Discord platform. And I think that also ends the program for today, and hope to see you back tomorrow. Bye.
Thank you. Bye.